Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Linear Algebra 1. This is Chapter 3, Geometric Vectors, Lines, and Planes. Section 3.4 is Linear Independence, Dimension, and Basis. Specifically, this lecture, what we're going to do is give the new notion of linear independence, which will give us a way to define basis and dimension for arbitrary vector spaces. Let's get to it. All right, example 1. Consider some non-zero vector E. The first thing we're going to notice is if alpha is any real number and E is not 0, and we have that alpha times E gives us the zero vector, then from one of our previous videos, video 3.2.1, we have property 5, and the first theorem in that video says that if you have a product of alpha times a vector is 0, then either the vector is 0 or the number is 0. And because we're assuming our vector is not 0, that says that we must have that alpha is 0. Therefore, what that's going to start saying to us is the only way that we can write 0 as a linear combination of this non-zero vector is, of course, to have alpha equals 0. What that really says is any set of a single vector is what we're going to call linearly independent. If I can write a vector or a sum of vectors, right now it's just one vector, but if I can write some linear combination of a single vector equals 0, the only way I can do that is if the number is 0, we're going to say that that vector is linearly independent. If I can find a non-zero number where I can do that, then we're going to call it linearly dependent. We'll do that in the next example, example 2. 2 is going to point out if I have any other vector A which is collinear with this non-zero vector E, then we know from video 3.3.1 that there's a theorem right at the beginning that says there's a unique alpha, which is a real number, such that A is alpha E. Because this is non-zero, what we can do now is add alpha, because this is a vector, we can add the negative of this to both sides, and we get this guy. Example 2, what we're going to do is let U and V be non-collinear vectors this time, and consider 0 being a linear combination of U and V. What we're going to do is argue that immediately if we have non-collinear vectors, that alpha and beta must both be 0. Why is that? Well, assume that we have this linear combination, 0 is a linear combination U of V, and say alpha is not 0. Well, if alpha is not 0, we can find the multiplicative inverse of alpha and divide through. So we're going to move this guy to the other side by adding the negative of beta V. Similarly, if beta is not 0, then we can do the same thing and solve for V in this equation. And it says that V is a multiple of U, and that immediately tells us again that U and V are collinear, which is a contradiction to us assuming this. So we've used reductio ad absurdum in either case. What that says is both of the coefficients have to be 0 if I can write 0 as a linear combination of those two non-collinear vectors. This is what we're going to call linear independence. U and V, if they're non-collinear, they're linearly independent vectors immediately. Let's give the general definition of if given any set of n vectors, when do we call them linearly independent? All right, definition, a set of vectors v1 to vn is called linearly independent if and only if we have this condition. And there's a conditional in the conditional. So basically what we've got is if we have that 0 is a linear combination of v1 to vn, then the only way we can do that is if all those coefficients are 0. If we have that, then we call them linearly independent. So there's an if-then in the antecedent of the if-then. They're linearly independent if we have that. This implies that the only way we can write 0 as a linear combination of those vectors is if all of the coefficients are 0. Go back to the previous couple examples and watch those more closely, and that's why we've come to the conclusion of this is what we should call the definition linear independence. So the parasitic definition, normally in books they say it's dependent if they're not independent. That's not really helpful in most cases. So we're going to call v1 to vn linearly dependent. If we have that, we can write 0 as a linear combination of those vectors before we get to what a basis in general for a line and a plane and space and then any n-dimensional vector space is. We're going to do 3 properties of linear dependence. Property 1 says if 0 is in a set of vectors, this is always linearly dependent. You can't put the 0 vector in a set of vectors and have independence. This is good to know. You can't use the 0 vector if you want it to be a basis. Property 2 says if you have a set of vectors which has a linearly dependent subset, then that set itself has to also be linearly dependent. You can't have a subset which is dependent and then add vectors and be independent somehow. Property 3 says that a set of k vectors is linearly dependent if and only if one of those vectors can be written as a linear combination of the other vectors. All right, the proof of these 3 properties go like this. They're not too bad, and it's good to spend time meditating on these horrible definitions. So this is why I go through the proof of these basic properties. From the definition of linear dependence, if 0 is in some set of vectors, I don't care what the other ones look like. Cleverly, what we do is use the number 1, which is not 0, and use that as the coefficient for 0, and then use 0 for all of the coefficients of the other vectors, which may be 0 or non-zero. But if I use 0 for all of these are going to be the 0 vector. When I add the 0 vector to those, I'm going to get 0. 1 times the 0 vector is 0, so I can cleverly write 0 as a linear combination of those vectors, where at least one of those coefficients is not 0, and that's our definition of linear dependence. So anytime you put 0 in a set of vectors, it's never going to be a basis because they can never be linearly independent. That's going to turn out what happens later when we want to define a basis. It has to be linearly independent and span all of space. Property 2 says that if I take a set of k vectors, but some subset m of them, say the first m I've re-indexed if possible, just put all the ones that are dependent at the beginning and re-index them, and then the other ones might be independent. We don't know. That's what we're trying to show. But if these guys are dependent, then we know that we can write 0 as a linear combination of those guys, and at least one of those alpha i's is not 0. Then what we cleverly do is just use zeros for, just like we did in the first one, use zeros for all of these other guys as the coefficients, and those will all be 0, and we know this sum is in fact the 0 vector, so we get that the 0 vector is a linear combination of all of the vectors, and at least one of these alpha i's still is non-zero, and that means that we have that whole set is linearly dependent. So you can't add more vectors to a dependent set and magically get independence at some point. Property 3 is Mark says that you should do this one direction and then the other direction, because a biconditional statement is 2 conditional statements. But I'm going to be lazy and use the if and only if. So if we have, this is one of the vectors depends linearly on the other vectors. So assume that. If I have that, then bring this guy to the other side, and I would get that alpha 1 plus dot 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 plus negative 1 when I bring this guy over is equal to the 0 vector. But negative 1 is not 0, so we get dependent. So if I can write v1 as a linear combination of these other vectors, we see immediately, because negative 1, when I bring it to the other side, that coefficient is non-zero, we get that 0 is in the span of all of those vectors, and one of those guys is non-zero, so we get dependence. On the other hand, if we start off with this condition and say, if we can do this where at least one of those guys is non-zero, then what we can do is solve the other direction and solve for this alpha I guy to be not 0, and get, in fact, that one of those guys, at least one of those guys, can be written as a linear combination of the others. That was the lazy version of the proof of the biconditional, right? Theorem 1, I'm going to do Theorem 1 and Corollary 1, Theorem 2 and Corollary 2, Theorem 3 and Corollary 3, which is going to give us basically what the dimension and basis for a line, a plane, and space is. I'll do the actual proof because I've already secretly done the proof once. It was the very first example we did. But I'll do the proof of 1, and then I'm just going to state Theorems 2 and 3 and their corollaries, and you can look at Dr. Solomonovich's textbook if you want to get the gory details of the rest. Theorem 1 says, let E be any non-zero vector. Then 1, the set consisting of a single non-zero vector is always linearly independent. And if I have two vectors which are collinear, i.e. in the same line of vectors, therefore they're collinear, then they're automatically, a set of those two vectors is automatically linearly dependent. And then corollary, why is that useful to us? The corollary 1 says, as an immediate consequence of this theorem, the maximum number of linearly independent vectors in a line of vectors is 1. And this is why a line is one-dimensional. That's going to be the definition of dimension in a second. How do we prove this? We already did it, but if I have that E is non-zero and somehow I have that 0 is a linear combination of alpha E, then by one of our properties of vectors, this says that alpha must be 0, and therefore, by definition, E is linearly independent. The only way I can get 0 as a combination is if all the coefficients are 0, therefore linearly independent. Condition 2 says, if I have that these two guys are collinear, we had a theorem which tells us that there has to be a unique alpha such that A is alpha E, and solving for bringing this to the other side, we get A minus alpha E is 0, or 1 times A plus negative alpha times E is equal to the 0 vector, so I can write 0 as a linear combination of A and E, and at least one of those guys, 1, is not 0. Therefore, this set by definition is linearly dependent. That's the proof of the theorem, of course, not the corollary, sorry. Therefore, as an immediate consequence of the proof of this theorem, we have a corollary which says the maximum number of linearly independent vectors in a line of vectors is 1. If you have 1 which is non-zero, he's independent automatically. And if you take 2 in that line of vectors, they're automatically collinear, therefore they are automatically dependent. Theorem 2. Theorem 2 is doing this for a plane of vectors now. If u and v are non-collinear, remember that means they're not the same direction. That's the key for this. If I first of all consider the set of u and v and they're non-collinear, any two vectors can be brought into the same plane, so they're coplanar. You just bring their initial points together. This you also have to remember. So they're coplanar, but they are non-collinear, so they're not in the same direction in the plane. Once I have that, that set of two vectors which is non-collinear must be linearly independent. This was example 2 essentially. And then I cheated and didn't do the second half. This is what we did in a previous video, but I'll recap it right here quickly. What it now says is those two vectors are automatically coplanar, but they're non-collinear. If I now take a third vector w, which is coplanar, laying in the same plane as those first two vectors, then the set of those three vectors must be linearly dependent. And as a corollary, quickly, what that really tells us is the maximum number of linearly independent vectors in a plane of vectors is 2. And that will be why a plane is two-dimensional. What's the proof of the theorem? 1, if I take u and v are non-collinear, then we saw by example 2 that if I try to say alpha u plus beta v is 0, then alpha has to be 0, otherwise I can write u as a multiple of v, which is a contradiction because they're supposed to be non-collinear, and this would say that they are collinear. If beta is 0, then the same thing, v is a multiple of u, which is bad because they're supposed to be non-collinear, so in either case we have a contradiction. So the only way I can write alpha u plus beta v equals 0 is if both of those coefficients are 0, and that's our definition of linearly independent. Condition 2 is a little more tricky, but here's the picture essentially. I have u and I have v. And say, first of all, there's a caveat. If w is collinear with either u and v, then you can just use that single multiple and then use a 0 coefficient for the other guy, and they're automatically linearly dependent. But assuming w is in some general direction which is not collinear with u or v in the plane, then I create cleverly this parallelogram. The parallelogram is one of the sides is some multiple of u, and then the other side is some multiple of v. So once I have that, if they're collinear, if u, v, and w are coplanar and u and v are non-collinear, then we create this parallelogram with sides alpha u and beta v. Once I do that, w becomes the diagonal of that parallelogram. And then we also saw in a previous video, if I do this plus this, it equals that diagonal. So the diagonal is in the span of those two vectors. So I can write w is alpha u plus beta v using this construction in general. And what that tells me is 1 times w, I can bring everybody to the other side, and I have that a linear combination of those three vectors is 0, and at least one of those guys is non-zero, the coefficients, and that says by definition linearly dependent. Therefore, as an immediate consequence, corollary 2 is now telling us that the maximum number of linearly independent vectors in a plane is 2 vectors. Let's do theorem 3. Right, theorem 3, hopefully you see where I'm going with this. Let u and v and w be non-coplanar vectors, but they're co-spatial vectors, I guess. The terminology runs out right away. 1. If I take any 3 non-coplanar vectors, they're in space now, but they're not laying in the same plane. 2 of them always will be. There's at least a third one sticking out of the plane now. Non-coplanar. They must be linearly independent. And the argument would be similar to part 1 of the theorem 1 and 2. 2. If A is any other vector in space, then the set u, v, w, a, by adding that is going to give, or more vectors, is going to always give linear dependence. And as a corollary, I'm not going to prove this one finally. Look at Mark Solomonoff's book for the details specifically. Corollary 3 is going to tell us now that this is why we call space three-dimensional. The maximum number of linearly independent vectors in space is 3. And this is, you'll see right away in the next scene, we're going to define what dimension and basis for any vector space is. Let's do that. All right, we got a couple more definitions and then our main theorem, which tells us a basis is that object we're looking for, which means that we can describe every vector in that space, vector space as a unique linear combination of those basis vectors. First of all, what's a vector space? Remember, a vector space is a set of objects with two linear operations of addition and scalar multiplication, and then we have an additive identity called the zero vector usually, and then a scalar identity called 1. And then if we look at those 10 axioms that we have, or 10 properties, if they satisfy that, we call that thing V a vector space. Then we call that vector space n-dimensional if it does contain first, and this is exactly what we've done. Go back and look at the previous videos for basis for a line and a plane of vectors and a basis for the space of vectors. What we're doing is, first of all, it must contain a set of n linearly independent vectors, and then any set of n plus 1 vectors or more has to be linearly dependent. Then we call the vector space n-dimensional. In other words, the dimension of a vector space V, denoted dim V, is the maximum size of a linearly independent set of vectors. The other definition we have now is any set of n linearly independent vectors in an n-dimensional vector space is what we call a basis of that vector space. Why do we want that? Theorem n now tells us a basis of a vector space V spans V, which means now that it's linearly independent, and it spans the space, which means every vector in V can be written as a linear combination. Not only that, linear independence, if you look at the proof, guarantees that this linear combination is unique. So we want a basis for an n-dimensional vector space because a basis will allow us to describe every single vector in that vector space as a unique linear combination of those basis vectors. Let's give one more definition and then remark. I know, but just a second, we'll recap. Now what we're doing is generalizing the notion of where you get coordinates in an n-dimensional vector space. Let V be a vector space and let B be a basis. I'm going to call it B for brevity because I don't want to write it down there. I don't want to write that symbol. So let B be a basis of that vector space V. If A is any other vector in that space, then A, the theorem just showed us we can write, not only can we write A as a linear combination, it's unique, so then there's no choice. And once I write A as a linear combination of those basis vectors, A with respect to the basis B has coordinates alpha 1 to alpha n. Or in other words, the coefficients in this linear combination of the basis vectors are called the coordinates of A with respect to that basis B. If we change the basis, we have to change the linear combination, and then its coordinates will change with respect to another basis. But essentially, long story short, we're not done yet. I'm going to do a couple more examples to show you how we're going to use Gaussian elimination to answer this question eventually. It's much easier. You can ignore the whole video and then just use this last bit. We'll put up a timestamp. A basis is a linearly independent set of vectors which spans the entire space. So a basis has two conditions. It has to be linearly independent and it has to span the space. Checking linear independence is much easier, so if you have a choice, always check independence. Let's do an example. All right, to finish off, example 3, decide if each set of vectors is a basis for the plane of vectors, which we call R2. The first set of vectors I have is 2, 5, 3, 7, and the set of vectors I have is 2, 4, and then 3, 6. Either way, in both cases, we're given two vectors, so this is the right number of vectors which can be a basis. What we're going to have to check is those two vectors can only be a basis if they're linearly independent. How do we check that? I'm going to phrase this as a linear homogeneous system, and then augment that system, use Gaussian elimination to REF, and then answer the question of yes independent or no independent. If I have independence, these two vectors are immediately a basis. So let's get to it. 1. If these vectors, call this V1 and V2, so that you can see algebraically now I've got coordinates, but these are my basis vectors. If they are linearly independent, what's the definition of linear independence? I have to have that alpha 1 V1, or let's call it for convenience x, x1 v1 plus x2 v2 has to equal the zero vector. What does that mean? If I have that, the only way that that can happen is if x1 equals 0 and x2 equals 0. Or I have the unique trivial solution. Now if I put those coordinates in, you can see that this is a 2 by 2 homogeneous system. So if this 2 by 2 homogeneous system has the unique trivial solution 0, 0, I can say yes independent and therefore yes a basis. Let's check that out. x1 times v is 2, 5 plus x2 times 3, 7 is v2. Has to equal the zero vector 0, 0 if and only if I get the system 2, 5, 3, 7 equals 0, 0. I augment the matrix. I row reduce now. However I want to do this, I have to get to REF. Doing this, go back to chapter 1 on how to do Gaussian elimination, but I am not lazily going to divide by 2 in this row or divide by 5 in this row. 5 minus 4 is a 1. So I'm going to multiply this row by -2 and add it to row 2. So what am I doing? Row 2 goes to row 2 plus -2 times row 1. What is that going to give me? That's going to give me 2, 3, 0. I didn't change that. And then 5 minus 4 is 1, and 7 minus 6 is 1, and 0 minus 0 is still 0. Now what I can do is interchange those. Interchange row 1 and 2. That gives me 1, 1, 0, 2, 3, 0. Then I'm going to get rid of that by doing row 2 goes to row 2 plus -2 times row 1 again. And that will give me 1, 1, 0. 2 minus 2 is 0. 3 minus 2 is 1. And then what does that give me? A much simpler system. This is now REF. I stop and make a decision when I'm in REF. What that tells me is, what does that say? That says 1 times x2 is 0, or x2 is 0. But now this says x1 plus x2 is 0, but that is a 0, so that tells me that x1 is also 0. So I have the unique trivial solution to this linear system, which means that yes, they are linearly independent, and therefore yes, they are a basis of space. So now what you're going to have to do is ignore the rest of this entire video. Don't tell Mark I told you that. But the way I check linear independence eventually is creating this homogeneous system, finding out in REF whether I have the unique trivial solution. If yes, and I have n vectors, this will be yes, they're independent, therefore if and only if yes, they span, and yes, they're a basis. Let's check the other one. If A and B are linearly independent, again, this is if and only if by definition alpha 1A plus alpha 2B equals 0. Notice that I'm arbitrarily calling them A and B this time instead of V1 and V2, and then I've changed my x1 and x2 to alpha 1 and alpha 2. It doesn't matter what you call them. You have to see that if I have two vectors, they have coordinates, and I'm looking for the unique trivial solution. I don't care whether you call it x1 and x2 or alpha 1 and alpha 2. The point is I want the unique trivial solution. That's the definition of linear independence. Again, when I have that, that's going to turn into, once I have coordinates, and I use the definition of scalar multiplication and addition, I'm going to get this system. I augment that system into this augmented matrix, and then I row reduce it to REF, and then I make my decision. In this case, I can see that if I do -2 times this one, I can kill the bottom row. And what that's going to say is row 2 goes to row 2 plus -2 times row 1. This time what that gives me is 2, 3, 0. And then I'm going to get 4 minus 4 is 0, and 6 minus 6 is 0, and 0 minus 0 is 0. What that tells me, if you really want, we can do row 1 goes to 1/2 row 1, and we're going to get 1, 3 over 2, 0, 0, 0, 0. This is now REF, so is that. But either way, once I have REF, what this tells me is, this row of 0 says that x2 is free to be any real number, and then x1 is going to be -3 over 2t. What that tells me is we have infinitely many solutions, which is not the unique trivial solution. Therefore, they are not linearly independent. Therefore, they are not a basis of 2 space. Please subscribe right here. I'll see you next time.